Hello, today I'm going to guide you through a comprehensive cardiovascular analysis using the iTFlow software, which leverages 4D Flow MRI technology to visualize and quantify blood flow within the heart. We'll examine both the left and right ventricular systems. The data presented here belongs to a healthy volunteer and can serve as a reference index for each measurement. iTFlow is capable of isolating specific parts of the heart for closer examination. For example, in the left ventricle, we use Streamlines to visualize the direction and velocity of blood flow within the ventricular system. These streamlines help us identify patterns and anomalies during the cardiac cycle, providing insights into the functional aspects of the heart. Next, we examine a 2D long axis view or a 3-chamber view of the left ventricle. These 2D streamline and velocity vectors offer a detailed look at the intraventricular flow and vortex formations and help pinpoint regions of abnormal flow or potential obstructions within the heart chamber. Pathlines trace the trajectory of individual particles over time, offering a dynamic perspective on fluid movement. By utilizing pathlines, we gain a more detailed view of local flows. By looking at the end diastolic volume and systolic volume, ejection fraction, stroke volume, and cardiac output together with pathlines, we gain a better understanding of what is going on within the heart. Here, we analyze the flow through the aortic valve, measuring the rate and kinetic energy of the blood ejected from the left ventricle. This data is crucial for evaluating the function and health of the aortic valve, including any regurgitant flow, which would indicate energy loss. Focusing on energy loss within the left ventricular system, we quantify how much energy is lost due to turbulent blood flow, which can be an indicator of cardiovascular health problems or inefficiencies in blood flow. The energy loss in this example is minimal, reflecting the healthy volunteer's uniform blood flow. Further breaking down energy loss, we compare it against metrics like body surface area and stroke work. These calculations help us understand the overall work efficiency of the heart and identify areas where energy is not optimally used. Now we switch our focus to the right ventricle. We observe streamlined patterns similar to those in the left ventricle, but focus on pulmonary circulation. Once again, we trace pathlines within the right ventricle, assessing the volume of blood inside the heart at certain points and the volume of blood flowing out of the heart. Examining the pulmonary valve, we measure the flow rate and kinetic energy as blood moves into the pulmonary artery. This data is vital for assessing the health of the pulmonary valve and the right ventricular output. Lastly, we quantify energy loss in the right ventricular system, identifying any inefficiencies that could suggest underlying health issues or the need for further medical evaluation. The volunteer experiences some higher energy loss on the right side. However, it is not sufficient to cause any medical issues. In conclusion, iTFlow software provides a powerful suite of tools for detailed analysis of cardiovascular dynamics, focusing on both ventricular systems and including detailed observations. This enables us to diagnose, evaluate, and monitor patients with precision and improve clinical outcomes.